Water flowing downhill makes sense. Water climbing back uphill on its own doesn't. Yet that's exactly what happened here, in a valley in ancient Turkey. No pump pushed it, no bridge carried it the entire way across. Roman engineers built something stranger instead, a sealed stone pipeline that let pressure do the work gravity couldn't. No concrete bonded the joints, no machine lifted the stone. Quick question before we dive in. Where are you watching from today? Most aqueducts solved a valley by going over it. This one solved it by going through it, using nothing but pressure. Aspendos sat in Pamphylia, a Roman region along the southern coast of what's now Turkey. Like every growing Roman city, it needed a reliable water supply. Engineers found a source, planned a route, and began the long process of designing an aqueduct to carry that water into the city. One stretch of the route caused a serious problem. A wide valley sat directly in the path, and much of the ground there was swampy and unstable, saturated with water year-round. Standard Roman practice usually called for a soaring arched bridge in situations like this. Build tall enough and gravity carries water smoothly across the gap, arch after arch, all the way to the far side. Here, though, that approach carried real risk. Unstable, waterlogged ground makes a poor foundation for a massive stone structure. Piers sinking unevenly could crack the entire aqueduct, undoing years of careful engineering elsewhere along the route. An inscription survives from the site crediting a wealthy citizen named Tiberius Claudius Italicus with funding this particular project. Records suggest he spent roughly 2 million denarii, an enormous sum, to see the aqueduct completed. That kind of investment meant failure wasn't really an option. Whatever solution engineers chose had to work reliably, and it had to survive for generations. So, instead of forcing a standard bridge onto unsuitable ground, Roman engineers here chose something considerably more ambitious. Rather than fighting the valley's terrain, they'd work with the physics of water pressure itself. This approach wasn't entirely unprecedented. Roman engineers elsewhere had experimented with similar pressurized systems, called inverted siphons, though the technique remained relatively rare. Most aqueducts throughout the empire still relied on straightforward gravity flow across elevated bridges. Choosing this path at Aspendos meant accepting serious engineering risk. Get the pressure calculations wrong, and joints could burst under strain. Get the construction wrong, and the entire system could fail catastrophically, wasting years of labor and enormous sums of money. Still, engineers moved forward. Perhaps the swampy valley genuinely left no better option. Perhaps ambition simply outweighed caution. Whatever the exact reasoning, workers at Aspendos were about to attempt something most Roman engineers throughout the empire never dared try. They couldn't build up. So they built down, and let the water do something almost nobody expected. An inverted siphon works on a deceptively simple principle. Instead of one continuous elevated channel spanning an entire valley, water enters a sealed pipe at the top of one hillside. Gravity pulls it downward, gaining pressure as it descends toward the valley floor. That pressure becomes the key to everything. Once the pipe reaches its lowest point and begins climbing the opposite hillside, built-up pressure forces water upward again, essentially pushing it back uphill without any external pump. Engineers call this the principle of communicating vessels. Water seeks its own level, and if a sealed pipe connects two points at similar elevation, pressure alone can carry water between them, even across a dip in the middle. Understanding this concept was one thing. Building a pipe capable of handling that pressure safely was an entirely different challenge. Workers quarried limestone locally from the eastern side of the nearby Eurymedon River. Stonemasons then carved this material into thousands of individual blocks, each one shaped with a precise cylindrical bore running straight through its center. More than 3,400 of these perforated blocks eventually formed the complete pipeline. Each block needed to align almost perfectly with its neighbors, creating a continuous channel capable of containing pressurized water without significant leakage. Sealing these joints required a specific solution. Workers used a mixture of lime and olive oil, applied where blocks connected. This particular compound expanded slightly when exposed to moisture, tightening the seal exactly where engineers needed it most. This wasn't concrete in any traditional sense. No aggregate, no traditional Roman cement mixture bonding everything into a solid mass, just carefully fitted stone and a specialized sealant designed for one specific job. If you're finding stories like this fascinating, hit subscribe. We cover ancient engineering feats like this every week. Picture the scale of this undertaking. Thousands of matching blocks, each individually carved, each requiring precise alignment with dozens of neighboring pieces, forming a pipeline stretching well over a kilometer across difficult terrain. Every joint represented a potential failure point. Get even one connection wrong, and pressurized water would find that weakness eventually, forcing its way through a crack or gap that compromised the entire system downstream. Roman engineers understood this risk intimately. That's likely why the sealing technique received such careful attention, using a compound specifically chosen for its expanding properties under wet conditions. Fitting the pipe together was one challenge. Making it survive the pressure building up inside it was another problem entirely. Pressure inside an inverted siphon isn't a minor engineering detail. It's the entire mechanism holding the system together or potentially tearing it apart. As water descended into the valley and began climbing the far side, pressure inside the pipeline increased dramatically. Comparable Roman siphon systems elsewhere have been calculated reaching pressures up to 19 bar, an intense force by any measurement standard. Roman engineers had no pressure gauges. No modern fluid dynamics equations existed to calculate exactly how much force a given pipe design could safely withstand. What they had instead was accumulated practical knowledge, careful observation, and a willingness to build in redundancy where uncertainty demanded caution. Two massive structures marked critical points along this pressurized route. Engineers built hydraulic towers roughly 30 to 40 meters tall, positioned at key locations where water direction changed dramatically. These towers likely served multiple purposes, though their exact function remains genuinely debated among researchers studying the site today. Some theories suggest they helped manage pressure surges. Others propose they provided access points for maintenance or inspection. This uncertainty itself tells you something important. Even now, with modern engineering knowledge and detailed archaeological study, experts can't fully reconstruct every design decision Roman engineers made here. What remains clear is the fundamental achievement. Water genuinely climbed uphill through this system, powered entirely by pressure differentials built into careful pipe placement and elevation calculations. Consider what this required practically. Engineers needed to understand elevation changes across the entire route with remarkable precision, ensuring the pressure generated during descent would prove sufficient to push water back up the opposite slope. Miscalculate this relationship, and water simply wouldn't complete its journey. Too little elevation drop, insufficient pressure builds, too much pressure, and joints throughout the system risk catastrophic failure. Somehow, Roman engineers threaded this needle successfully. The aspendos siphon functioned as designed, carrying water reliably across a valley that would have otherwise required a massively expensive, structurally risky elevated bridge. This achievement represents something genuinely remarkable in ancient engineering. Roughly 1 in 20 Roman aqueducts throughout the entire empire incorporated this kind of pressurized siphon technology. Most engineers simply avoided the risk, sticking with more predictable, if more expensive, bridge construction instead. Aspendos stands as proof that some Roman engineers pushed considerably further, applying sophisticated pressure principles most of their contemporaries never attempted at this scale. The pipe held the pressure. Getting the stone that high in the first place was its own separate battle. Solving the hydraulic engineering problem was only part of what aspendos demanded. Someone still needed to physically construct 2 towers reaching 30 to 40 meters into the air, using thousands of heavy limestone blocks on ground that offered no particular advantages for construction work. Without mechanized cranes, moving these blocks required careful planning at every stage. Workers relied on rope and pulley systems, powered entirely by human effort, sometimes supplemented by animal labor where terrain allowed. Wooden scaffolding likely played a critical role, though direct evidence for its exact design at Aspendos remains limited. Based on similar Roman projects, engineers probably built temporary wooden structures alongside the rising towers, providing workers safe access to increasingly higher sections during construction. The swampy valley floor added another layer of difficulty entirely. Building stable foundations in waterlogged ground required different techniques than construction on solid bedrock. Engineers likely needed to reinforce foundation areas significantly, perhaps using deeper footings or specialized drainage solutions to prevent towers from settling unevenly after construction finished. Uneven settling could crack pipe joints, undermining the entire pressurized system's integrity. Transporting materials across this same difficult terrain compounded the challenge further. Moving thousands of heavy stone blocks across soft, unstable ground likely required temporary roadways or platforms, adding significant preparation work before actual construction could even begin. None of this happened quickly. Coordinating workers, managing material logistics, and maintaining construction quality across such a technically demanding project likely stretched across years, not months. Every stage carried genuine risk for the laborers involved. Working at height using rope-based lifting systems left little margin for error. A snapped rope or miscalculated pull could easily result in serious injury for workers positioned near heavy suspended stone. Coordination among large labor teams became essential, much like other major Roman infrastructure projects throughout the empire. Workers needed to move in careful unison, particularly when lifting or positioning especially heavy blocks destined for the upper sections of each tower. Consider the layered difficulty here. Engineers weren't just solving one hard problem. They were simultaneously managing complex hydraulic calculations, difficult terrain, dangerous vertical construction work, and enormous logistical coordination, all without any mechanized equipment to lighten the physical burden. Every one of these challenges had to be solved correctly and solved together for the final system to function as intended. Every block had to go up by hand. Get the foundation wrong in this soft ground, and none of it would matter. Completed, the Aspendos Aqueduct stretched roughly 17 kilometers from its water source to the city itself. Most of that distance used more conventional Roman techniques. Buried masonry channels carried water underground through stable sections of terrain, while occasional bridges and short tunnels handled smaller elevation changes along the broader route. The real spectacle, though, sat in the final stretch before reaching Aspendos. Here, the famous inverted siphon crossed the wide, swampy valley that had presented such a serious engineering challenge from the very beginning. This siphon divided into three distinct sections. The first stretch ran 592 meters, carrying water down toward the valley floor. A second, longer stretch extended 924 meters across the lowest section of terrain. A final 154-meter segment carried water up toward its destination on the opposite side. Two hydraulic towers connected these three sections, marking the points where water's direction shifted dramatically, first descending, then eventually rising again under built-up pressure. Standing at ground level today, visitors can still see substantial remains of both towers, along with sections of the perforated limestone pipe that once carried pressurized water across this same challenging landscape. Once operational, this system delivered water reliably into Aspendos, supporting a thriving Roman city in Pamphylia. Public fountains, baths, and private households all depended on this continuous supply, made possible by an engineering solution most Roman cities never needed to attempt. The achievement extended beyond simple functionality. This represented genuine confidence in hydraulic principles, applied at a scale few other Roman engineers throughout the empire dared replicate. Local officials and citizens likely viewed the completed aqueduct with considerable pride. An inscription honoring Tiberius Claudius Italicus for funding this project suggests the community recognized just how significant an achievement this actually was. For a Roman city positioned along a rugged Mediterranean coastline, reliable water access meant genuine prosperity. Agriculture, public health, and daily civic life all depended on this kind of dependable infrastructure functioning correctly. Engineers had promised a solution to a genuinely difficult problem, and delivery matched that promise. Water flowed exactly as calculated, crossing an unstable valley using principles most contemporaries considered too risky to attempt. Aspendos stood as proof that ambitious engineering, backed by careful calculation and substantial financial investment, could solve problems that more conventional approaches simply couldn't handle. It worked exactly as designed. It just didn't get nearly as long a life as its builders probably expected. Evidence buried within the ancient pipeline itself reveals something important about how long this remarkable system actually operated. Mineral deposits called sinter build up gradually inside water channels over time, layer upon layer, as dissolved minerals slowly accumulate along interior surfaces. Researchers studying the Aspindos siphon measured this sinter thickness carefully. Their findings suggest the system functioned for no more than roughly 150 years before suffering significant damage. That's a relatively short lifespan considering the enormous investment and technical achievement involved in building it. What caused this eventual failure remains somewhat uncertain, though evidence points toward possible earthquake damage. This region experiences seismic activity periodically, and a significant tremor could easily have cracked pipe joints or shifted tower foundations enough to compromise the entire pressurized system. Once damaged, repairing an inverted siphon presented serious challenges. Unlike simpler infrastructure, this system required precise pressure calculations and careful joint sealing throughout its entire length. Partial repairs likely couldn't restore full functionality without addressing the complete pipeline. Here's where the story takes a genuinely unexpected turn. Centuries later, builders constructing a different bridge near Aspindos reused materials from the damaged siphon. Some of the same perforated limestone blocks, originally engineered to withstand extreme internal water pressure, ended up repurposed as simple structural material. Stone that once channeled pressurized water uphill through careful hydraulic engineering found new purpose supporting foot and cart traffic across a completely different structure entirely. This kind of technical achievement, building a functioning pressurized siphon at this scale, remained genuinely rare throughout the Roman world. Only a small fraction of aqueducts across the entire empire incorporated similar inverted siphon technology. As the Western Roman Empire eventually declined, so did much of the specialized engineering knowledge required for projects like this. Building techniques requiring this level of precise pressure calculation, without modern measurement tools, simply stopped being practiced or taught as widely as more conventional construction methods. Modern hydraulic engineers studying Aspindos today still express genuine admiration for what these ancient builders accomplished. Understanding pressure dynamics well enough to build a functioning siphon at this scale, using only stone, careful measurements, and accumulated practical knowledge, represents impressive technical sophistication. Some questions about the exact engineering reasoning behind specific design choices remain unresolved even now, studied by researchers using modern analytical tools the original builders never had access to. The pipes that once forced water uphill under enormous pressure ended their days holding up a bridge instead, a second life nobody engineered for, no concrete, no modern machinery. Just fitted stone, a hand-mixed seal, and enough understanding of pressure to make water climb uphill on its own. Aspindos remains proof of how far ancient engineering could go. If you enjoyed this story, hit subscribe for more lost construction history.